Hello students, in the last topic we discussed about the RMS value and mean value of AC. Now DC can flow through a resistor, flow through an inductor, flow through capacitor. Nothing will happen because the charge simply flows. The current or voltage doesn't vary as sine function or cos function. As a result, the charge flows through these devices. The device will show some opposition, some resistance. That's it. But when AC flows through the devices like inductor, capacitor and resistor, since the AC varies according to sine wave or cos wave, there will be a change in the phase or change in the pattern of the graph. Phase means angle. There will be a change in the angle between the voltage and the current. That is what we are going to discuss in this chapter. So I say once more, when DC flows through any of the components, there will not be any change of phase. But when AC flows through the components, different components, there will be a change in the phase. So let us first discuss what happens when AC flows through a purely resistive circuit. E is equal to E0 sine omega t. That is the instantaneous value of AC. Now E is E0 sine omega t and we know I is equal to E by R. And instead of E I can put E0 by R. Instead of E I can put E0 sine omega t. So E0 sine omega t divided by R. And I put E0 by R in the bracket, and you already know E by R is called resistance. So what is E0 by R? I0. So finally you can get I is equal to I0 sine omega t. Now compare the equations for the EMF and the current. That means these two equations. Compare these two equations. E is equal to E0 sine omega t and I is equal to I0 sine omega t. What is the phase for both? What is the phase angle for both? Look, here also it is omega t, here also it is omega t. So the phase angle for both is omega t itself. That means when current flows through a resistor, purely resistor, current and voltage are in the same phase. Therefore we can write, when I draw the graph, it will be like this. Blue stands for EMF and the red stands for the current. The graph will be like this, the same sine wave. So their starting point is same. They reach the maximum value at the same time period, that is t by 4, and again they come to 0 at the same time, like that. Both of them behaves in the same pattern. That is why we say current and voltage are in the same phase. And you can draw, so this is the graphical representation. What I showed just now, this will be the graphical representation. And to represent it in a vector form, we use current as one vector and voltage as another vector. And when we draw the diagram connecting that current and voltage, we say such diagram as phasor diagram. So phasor means it is a vector which rotates about the origin with an angle theta. So since current and voltage are varying alternatively with time, we can represent current using one arrow and voltage using other arrow, and you will be representing the angle between them. Such kind of diagram is called phasor diagram. It is easier to represent than the graphical method. You can just see, I just draw x-axis and y-axis, and the current I marked with the red arrow and EMF I marked with the blue arrow. Both of them are in the same direction itself, and angle between them is omega t. So seeing this phasor diagram, you can very well know that current and voltage are in the same phase and their phase angle is omega t. That's the easiness of phasor diagram. Now let us see what happens when current flows through a purely inductive circuit. Pure inductor. Pure inductor means inductor without resistance. Actually, that is not possible because when we make an inductor, inductor is made up of copper coil and copper coil is having a resistance. So, there will be a resistance in actual practice, but we take the ideal case where there is only inductor. Now, AC is applied across the inductor. You can see the figure. So, E is equal to E0 sin omega t. That is the instantaneous value of EMF. Now, the alternating current is passing through the inductor. Current is continuously varying. What happens when the current continuously varies? There will be a change in the magnetic flux. Obviously. So, due to the change in the magnetic flux, EMF will be induced in the solenoid and that EMF is called back EMF or self-induced EMF. So, we will go with the derivation. E is equal to E0 sin omega t, and I told when it passes through the inductor will produce back EMF, and that back EMF, that means that induced EMF is given by minus L into di by dt. So, in order to maintain the flow of the current, the applied EMF must be equal and opposite to the self-induced EMF. Only then the current will flow. So, I will write E is equal to L into di by dt. So, that minus sign goes because it should be equal and opposite. So, there is a negative sign here. I again put one more negative sign to show it is equal and opposite. So, minus minus cancels. Therefore, I got E is equal to L into di by dt. And instead of E, I can put E0 sin omega t. So, E0 sin omega t equal to L into di by dt. Now, what we are going to do is keep only di here. Everything has to be taken to the other side. So, di will stay here, L will go to the other side. So, it will be E0 by L. And dt also will go to the other side. So, it is into dt. So, di is equal to E0 by L sin omega t dt. And that is di, a small current. So, how will we find the total current? Total current can be found by integrating. So, total current I is equal to integral E0 by L sin omega t dt. E0 by L is constant. I can take E0 by L outside, and integral sin omega t is minus cos omega t divided by omega. I will write it here. I is equal to E0 by L, that is a constant, into integral sin omega t dt. Integral sin omega t dt is equal to minus cos omega t divided by omega. That is the answer. So, we are putting that in the above equation. You will get I is equal to minus E0 by L sin omega t, cos omega t by omega. So, that is I is equal to minus E0 by L omega cos omega t. And cos theta is minus sin theta, or sin 90 minus theta is cos theta. So, I can write I is equal to minus E0 by L omega I is equal to minus E0 by L omega. Cos omega t can be written as sine 90 minus omega t. Sine 90 minus omega t is cos omega t. Then to remove, there is one negative sign here. There is one negative sign here. So when you take negative sign inside, it will be omega t minus pi by 2. So I will write the equation as I is equal to E0 by L omega sine omega t minus pi by 2. So that's the equation here. Now instead of E0 by L omega, I can write current. So instead of E0 by L omega, I put I0, which is the peak current. So the final equation becomes I is equal to I0 sine omega t minus pi by 2. Okay, so remember E0 by L omega is I0 because you already know current is equal to voltage by resistance. This L omega is actually the opposition shown by the inductor, that is equivalent to resistance. I can't say resistance because resistance is the property of the resistor. So I will just use the word opposition. So E0 voltage by opposition will give you the current. That is why I told E0 by L omega is I0. Now you look at these two equations. See, this is sine omega t. E is equal to E0 sine omega t. Here I is equal to I0 sine omega t minus pi by 2. So when you compare these two, what can you understand? One is omega t. Second one is omega t minus pi by 2. So current is lagging the voltage by an angle pi by 2. So when current flows through a purely inductive circuit, purely inductor, the current lags the voltage by an angle pi by 2. So how will I draw the graph? Let us see. So remember, current is lagging. So I'll first show the graph, then I'll show the phasor. So look at the graph. In the graph you can see, first you have to draw the EMF because E is E0 sine omega t. So first you have to draw the EMF as the sine wave, which is represented by the blue, and then you have to represent the current. Current is I0 sine omega t minus pi by 2. That means when EMF starts from 0, the current should start from a negative value. And when EMF reaches maximum, the current is 0. So the current graph always goes behind the EMF graph. That is why we say the current is lagging. Now see the phasor diagram. In the phasor diagram you can see it very clearly. First I draw EMF in the first quadrant. Its angle is omega t and current is lagging by 90 degree. If it is lagging, it has to be drawn in the fourth quadrant. If it is leading, we will draw that in the second quadrant. Okay, so this is the EMF. EMF will be always come here. EMF will always come here, and if current lags, we will draw downwards like this in the fourth quadrant. If the current leads, we will draw in this direction. Okay, so that's it, and I have marked pi by 2. So current lags by an angle pi by 2. Okay.